Okay, we're about to start. Welcome Venkat again. He will tell about another amazing things which everybody needs to know to be successful.
Thank you. Well, welcome to the talk on design patterns in the light of Lambda Expressions. I'm going to talk about how we can benefit from using design patterns, but also mixing lambdas with it. But before we get started, let's talk a little bit about design and design patterns. You know, as developers, we often are struggling to design the code and the software that we are designing. And especially among Java developers, I would say, we have this fascination towards using design patterns. But before we talk about using design patterns, let me first say that I really hate design patterns. I know that was very motivating, wasn't it? Okay, well, the reason I say that is, think about pie for a minute. We all know that grandma makes the best pie ever. And you've been telling your friends about grandma's pie for so long, and your friends come to you and say, if grandma makes such a wonderful pie, why don't you make that pie for us? We want to taste it and see how it is. And so what do? You call grandma and say, Grandma, my friends are coming home on Saturday. I've been telling them about your pie for years, and now they want me to make that pie. I need your recipe. And grandma gives you the recipe. And what do? You start writing the recipe down, and you tell grandma, slow down, tell me every single step. And grandma says, take some flour, add some sugar. And you're like, whoa, wait a minute. Tell me exactly how much flour and tell me exactly how much sugar to add. And grandma says, about 2. And you're like, wait, is it 2 spoons or tablespoons or teaspoons? And you write all this down and you ask grandma, what are the best practices? What are the do's and don'ts? And then after getting all this recipe, you start early that Saturday and you make that pie. How did that turn out to be? A disaster, wasn't it? The last time I tried something like that, I lost the spoon with it as well. And you go to the store, you get a pie, be done with the evening, and you meet grandma the next week and say, Grandma, your recipe is broken. It was a disaster. And grandma says, why did that end up that way? Why don't we make the pie while we talk? And you start noticing that grandma starts making pie, and what does grandma do? Grandma takes 2 teaspoons of sugar, measures it accurately, and puts it right? No. Grandma is having a good time talking to you and takes sugar and tosses it in. And you said, whoa, what was that? And grandma says, that was sugar. How much did you put? And grandma says, enough? And that's when you know grandma doesn't use the recipes that she gave you. Well, what I'm getting to is, there are these 4 guys who wrote the best ever written book on design patterns. These 4 guys are the grandparents of our industry. And the worst thing they ever did in their life is write the damn book. And everybody thought, oh my gosh, I can do this now. And they read the design patterns book, and we turn application into a monster after that. Now that I've so very well motivated you to look at design patterns, let's talk about design patterns. Well, what I really want to emphasize is that I love design patterns, but not for the reason a lot of people get drawn into it. I don't think design patterns are a real great design tool. I think design patterns are really good communication tool. I use design patterns to communicate with my fellow developers about the type of solution that I'm using in a given context. But the worst way to really use design patterns is to sit down at work and ask the question, I wonder what pattern I can use now. You know, when you're waking up in the morning, right as you're about to get off your bed, if the thought that comes to your mind is, I wonder what design pattern I can use at work today, I recommend you call the boss and say, I'm feeling very sick today, and just fall back on bed. There's no point going to work today. And the point really is, we should really see these patterns emerge in the code, and then, of course, apply them where it makes sense, but use it to communicate. But having said that, I feel that there are patterns we have been using for quite a while that can become a lot better. Now, I started programming a long time ago in languages like C++. And when Java came out, I had this amazing eagerness to use Java, partly because the design patterns I would use in C++ became a lot simpler when I started using them in Java. What were monsters in C++ were kind of baked into the language, and I was really happy. And to me, to live that happiness one more time in the language Java was amazing, because when Lambda expressions were introduced, I got excited one more time because the patterns I would write in Java became a lot more simpler again in Java thanks to these lambdas. And that's what I want to focus on here as lambdas as these design tools. So lambda expressions are really an interesting way to design and to be able to pass these anonymous functions through the application. So what do lambda expressions provide for us in general? I know you all know lambdas, but I'll put a little perspective on that with a little example right in here. So suppose, let's say we want to create a thread, and I'm going to say is equal to new thread. And then, of course, I'm going to just start this thread. All that I'm going to do is simply say in main to say that I'm still in the main thread. So when I run this code, you can see it's simply printed in main. Well, what about the other thread we just started? Well, for that, of course, you can say new runnable. And then within this, of course, you could write the method called run. And within the run method, you could say in another thread like this. And of course, when you run this, the other code ran in this other thread, as we can see in here. But when you look at this code is an example of a very high signal or very low signal to noise ratio. That's a lot of fluff, a lot of verbose code. But what are we really trying to do in this code? What we're really trying to do is to pass a piece of code, a function, to this particular thread. But we couldn't do it in the past because functions were not first-class citizens in Java. So we were treating functions like kindergarten children. This little kid comes to you and says, could I go to the neighborhood park, please? And you said, no, child, you cannot go alone. Let me send an adult with you. So we started wrapping functions within objects for no good reason. Well, it's kind of like, as a parent, I love watching my children grow up as adults and they go off on their own. It's kind of like watching that functions become these kindergartners and growing up and going on their own. And now, of course, what you can do is rather than writing all that fluffy code, you can simply take that little function that you have with you and you can treat it like it's an adult. So you can remove that little method we created right there. And we can remove all that noise around that code and keep removing. And then, of course, we can simply put that little lambda expression and write the code to pass it around just like that as we did before. So in this case, we can simply pass the lambda where we would have passed the object before, a single method object. So in other words, lambdas are anonymous functions, and we can pass these anonymous functions around to get our coding done. So this become a really nice way to design the code with these lambdas. Well, with that said, let's talk about some design patterns we could use. I'm sure almost everybody in this room at some point has written a strategy pattern. How did you write the strategy pattern? Just think about it. What does a traditional strategy pattern look like? In the traditional strategy pattern, you have a class that wants to vary part of its implementation. So to vary part of the implementation in a function, what would you typically do? You would pass an interface to it. And the interface would have a function that implements that little variation, and then you would create classes that implement that interface. So if you were to implement a strategy pattern, what do you normally do? You create an interface and a bunch of classes and have a corporate design meeting to talk about it. That's a lot of work to do strategy, isn't it? If all you're trying to do is to make a slight variation in a logic, why do you have to implement so much code? Well, lambdas can get rid of a lot of that. To entertain this thought, let's look at an example. Imagine that this is Friday evening, and you are at work still. And you know how our mind kind of turns off on that Friday evening. About 4 p.m., and you are getting extremely nervous and agitated because your body is at work, but your mind is not. You know that feeling, isn't it? You have that very important party to go to, and all your old friends are coming to town. You've been talking about this for weeks, and you're so excited you want to go to this party. But unfortunately, you have to get one piece of work done. And that is one of your colleagues, the one who nags you all the time, wants you to implement a function called something called total values, which is going to take all the values given in a collection and total it. So what are you going to do? You say, here's a list of numbers. We'll go ahead and say integer numbers. And I'm going to simply say equal to list of. Let's go ahead and say this is going to be list of numbers 1 to 10. And I want to just total all these numbers together. How do you implement it? Well, you're going to implement it. You're going to simply say static right here. And then you're going to say integer total values. This takes a list of integer. We'll call it as values. And what are you going to do within these values? Let's write the code in the traditional imperative style to begin with. We'll say total is equal to 0. We want to return the total when we are done with it. And within here, we'll say for int element coming from the values, all we are going to do is simply say total plus equal to the element given, and we will implement the code like that. So you finish this code, and you're about to go for this very exciting party. And before you could go, unfortunately, your colleague comes to you and says, oh, wait a minute. Not only do I need a function to total the values, I also need a function to total all the even values. And you take a deep breath and say, you mean in addition to total values, you also need total even values? And your colleague says, yeah, I need that, and I need it now. And you look at your watch, and you really want to go to this party. You're not very excited. And then you realize it's not really that bad, because most of the code you need is already done. So what do? You think about it for a minute. You stare at this code, and you tell yourselves, there's got to be a reason why they created copy and paste. I mean, if nobody should use it, why would they have a concept of copy and paste? In fact, it's so integral to what we do, we even have shortcut keys for it. A Control-C and a Control-V. How cool that is. So you copy and paste it really quickly, and you say total even values right here, and you simply say if the value of the element mod 2 is equal to 0, then of course you total it, otherwise just skip it. So you implement that code right away readily, and you have that working. And you're about to leave when, as the fate may have it again, your colleague comes to you and says, oh, I also need a total odd values also. Well, you know you're in trouble now, because copying and pasting a code a third time is an act of criminal negligence. But it's Friday evening, and nobody is watching. So what do? You quietly make a copy of this function one more time and copy it and paste it again. And then you call this as total odd values. And then you change this code to a not equal to, and you quietly slip away. But on the way to the party, guilt kicks in, because you just realize how terrible this is. And what if somebody looks at your code? What would they think of you? So immediately you pull by a nearest Starbucks and you start refactoring your code. But as fate may have again, some of your other friends are hanging around the same coffee shop. They come and talk to you, and before you could close your laptop, they take a look at your code and they get to know your dark side. And they never return your phone calls anymore. Why would anybody want to hang around with people who do copy and pasting for a living? Let's pretend this never happened. Shh. Quietly roll back the code like we never did this. So all the way back now, imagine you just wrote that code for that particular function, which is the total values. Now that that is done, your colleague comes to you and says, hey, I need one more function to total even values also. You ask your colleague, do you mean you want this total values, but you also need total even values? And your colleague says, yep, that's what I want, and walks away. Well, you don't just quite implement it. You look at the code and say, how do I reuse this code to make that happen? So what you're going to do to do this is, before you implement that code, you're going to implement the strategy pattern. So what you're going to do is look at this code and say, all right, we will take this code and we'll call the total values, but we'll do a little bit of refactoring. We'll introduce a second argument to this function, where the second argument is called a selector. And then we will say, if the selector test on the element is true, then total it, otherwise ignore it. Because when you notice the 3 duplicated code we had earlier, the only difference between the 3 pieces of code was what's within the if statement, so we can extract that as an argument to this particular function. So in this case, you said selector, and if the selector test is true, then total, not otherwise. Well, the question is, what in the world is that selector? Well, the selector, as it turns out to be, is actually a .function.predicate, and you can now simply say that you have a predicate right here where the predicate takes an integer and returns a Boolean response for the given integer. So now you can simply say that you can refactor this and say whatever element you are receiving, simply return a true as a response. Now what you can do is to refactor, having refactored that code, you can simply say, given an element, element mod 2 is equal to 0, then total it, otherwise ignore it. Now your colleague comes to you and says, hey, I need you to do one more function, total odd values. You tell your colleague, go back to your desk and do it yourself, because we made it so easy to reuse that code. We don't have to be duplicating the code over and over. So if you look at this code, what did we just do in this particular function? We created a strategy pattern. How so? Because this function total values provides the engine for the computation, but the strategy is determining what value to actually total. So in other words, you can use the predicate as a way to implement the strategy. But of course, you know that you can also refactor this code to a more functional style as well. So in this case, what you could do potentially is you can simply say return values.stream. And then in this case, of course, you can say filter, and you can just pass the selector to it. And then, of course, map to int, and given an element, simply return the element, and you perform the sum operation on it, and you can return the result as well, and you can refactor that to a functional style in this particular case. So in other words, if you really want to implement a strategy pattern, you don't have to invest your time and effort in creating interfaces and classes. You can simply use Lambda expressions and functional interfaces to get done. And the functional interfaces really are placeholders for the Lambdas. But the essence is that you really are keen in using the single function that you're able to use to really get your work done. And that becomes your strategy to provide fairly easily. So that gives you an idea about how you can use the Lambdas to implement strategies without much difficulty at all. Well, the next thing I want to talk about here is to delegate to a particular object creation to a later time. So before we talk about this, let's take a look at a slightly different example here just to entertain this thought. I'm going to use the Scala as an example here, but you could use different languages to illustrate this particular point. So here is an example in Scala. So let's imagine for a minute that I have a function called compute, where the function compute takes an integer, and all it's going to do is simply print out, let's say, called over here, and then I'm going to simply say over, in this case, let's say return n times 2. So the fact that I'm returning a number times 2 in the compute function, x equal to 4, I say if x is less than, let's say, 5, and the call to compute of x is greater than 7, I want to simply print out, let's say, path 1. Otherwise, what I want to do here is to print out, let's go ahead and say path 2. When I run this code, as you know, this code is not going to invoke the compute method if the value, well, if x is greater than 5, let's say, it's not going to invoke the compute method. But what if I really wanted to display the value of compute of x over here? Well, the good news is compute is not called still. But what if the value of x is greater than 5? Sadly, compute is called twice in this case, which is not very efficient. So to make this more efficient, you could move this to a temp, and you could then call temp right in here. And then, of course, you could simply assign temp is equal to, and assign the compute to this particular function. When you execute the code one more time, good news in this particular case is that you are not going to take the path 1, but the bad news is compute was called even though it's not needed. But of course, if the value of x is greater than 14, compute was called only once. That's a good news. But if x is not greater than 14, we call compute still, which is really unfortunate. So what do you do to prevent the call to compute when it's really not needed? Well, what you can do in the case of Scala is you can mark this as lazy. So without lazy, you notice that compute is actually called. But with the word lazy in place, when I run the code, notice compute is not called because it defers the evaluation until it's actually needed. So if I put a 14 over here, you can see it is calling compute, but with the 4, it is not actually calling it. It bypasses that. So this is a nice way to defer evaluation until you really need it actually. Now this is great because we can be efficient and not have to do process that is really not significant or needed. Well, but what about Java though? Unfortunately, Java does not have the facility to do laziness. Well, this is one of the places where I want to think about a way to delegate until we no longer really cannot postpone it. So how do we do this? So here is an example of that here in Java. So I could say public static, let's say void compute, or int compute rather. And I'm going to say in this case an input n. And all I'm going to do is return n times 2, let's say. And let's go ahead and output called. Now, obviously, this is a trivial function, but imagine this is time consuming. What are you going to do? So I'm going to say x is equal to 4 if x is, let's say, greater than 5 and the compute of x is greater than 7. I want to print out right here, we'll say path 1. Otherwise, we'll say else we'll print out, let's say, path 2. Well, the good news in Java is when I run this code, you can see compute was not called. But on the other hand, what if I were to save this into a variable called a temp, and then I say int temp is equal to compute? Unfortunately, the call to compute happened right now, even though we really don't need that value at all. So what do we do about it? Well, this is where we can engage laziness of evaluation. So how do we do this? Well, this is one of the places, again, where we can use a level of indirection. So what we can do here is we can say, well, temp is equal to not a call to compute, but we will instead pass a lambda expression to it. So in other words, what if rather than calling compute, what if we call a lambda, which in turn will call compute, but at a later time? So what we can do here is to say lazy, and this is going to be a lazy of integer, if you will, and then I'm going to pass to this lazy a lambda expression in the constructor. So in this case, we are creating an object called lazy, and we are telling the lazy object to receive a constructor call which takes the lambda. Then we can come here and call a get method on this particular object to receive the data. So how do we make this work? Obviously, the lazy doesn't exist in Java unless you're using something like Project Lambda. You have lazy, but otherwise, you may have to create one yourself. So what I'm going to do here is to create a class called lazy, which takes a type t, let's say. And then I'm going to write a private t instance, but I'm going to also keep a supplier of type t, we'll call it supplier. So we are going to bring in the java.util.function.supplier into the mix over here. So now that we have a supplier, our lazy contains a supplier and an instance of t. Then we can write the constructor for the lazy, where we take the supplier of t, we'll call it the supplier, and all I'm going to do is simply save the supplier equal to the supplier and put it away. Then I can create a public t get function where I can say if the instance is equal to null, then of course what I could do here is instance is equal to supplier.get and supplier equal to null. And then, of course, I can simply return the instance that we have. This is not thread safe, but my intention is not to make it thread safe, but that gives you an idea about how we are going to implement it. So the lazy class simply says, I'm going to check my instance to be not null. If it is null, I'm going to get the value from the supplier, save it into my instance, and then, of course, return the instance, whether it is there or not. So if I were to run this little example code, what's going to happen at this point? Well, okay, it's complaining that cannot convert an integer to this particular value, obviously because that becomes a lazy. So I'll just put a var over there, and now you can see it says path 2. Well, that's great. That's a path 2. It did not call the function. Let's go ahead and say over here, and execute the code. It's still path 2. But on the other hand, if x is 14, you can see that it's actually doing the call to the function. And again, if I really wanted to print the value that I have from the get, you will notice that it's not going to call the compute more than once. So you can see that it's pretty much doing what we intended to do. So in other words, we can use the supplier to postpone evaluations until a later time. So again, we can use lambdas to the rescue here, where the lambda is really being passed in for the supplier, and that becomes a level of indirection in the code. So we can use this within a way to postpone evaluations. We could also use this for implementing the virtual proxy as well. If an object is going to hold on to a reference to an object which is heavyweight, we can use a lazy to put the reference so the object comes to life if and only when we need the object, not otherwise. So we can implement very easily the virtual proxy. A virtual proxy is something I really like a lot. If you look at the design patterns book, for example, the proxy pattern is one of the most powerful patterns because it is used in so many different ways. Virtual proxy, remote proxy, control proxy, has smart pointers and so on. It's one of the most powerful patterns out there. But virtual proxy is dear to me because I remember working on an application a long time ago when we had written the code in a very simple way where our object was querying for certain properties in the system. Everything was working fine for a long time. And we were maybe about a week or so before releasing it when a developer came with a panic and said, oh my gosh, the application is extremely slow when I tried it on a particular system. And when we looked at it, what we realized was, in all our tests, unfortunately, we were using a small test data, and the program was working really well. But in this particular test environment, when we opened up the application, it literally had millions of data to process. And once it started going through the millions of data to process, our application was hanging up because it was trying to load up all this data. And of course, the panic ensues when you're close to production, and what do you do about it? Well, we sat down and thought about it and said, how could we get away with this without spending too much time and effort? And we came up with a fairly easy way to solve the problem. We literally took this object that was doing all this work and just renamed it. And we created another class with exactly the same name so the rest of the code would not have any trouble compiling. And then this outer new class we created with the name of the old class simply had a pointer to this particular reference to this object, but the reference was null. And then it would simply create millions of these, but those objects were not populated until the user clicked on a particular object on the screen, and that's when it'll go out and get the data. So in other words, it'll cache the data on demand, but not pre-create it. And within minutes, we had an application that was performing really well without too much code change in the system, simply moving this one level, and that was an application of virtual proxy. And the point again, we didn't sit to design to use the pattern. The problem posed itself. We devised a solution, and then when we came back and laughed at with each other and said, "Wow, that's amazing! How did we solve it?" Oh, darn it, we used virtual proxy to solve it. So that can be a very effective way. But similarly, you can now, of course, use something like a lazy to implement it very effectively if you want to. So that gives you an idea about how we can implement that particular feature. Well, the next thing I want to show you here is a decorator pattern. Now, I want you to just think about decorator pattern for just a minute. Do you remember the world-famous example of decorator pattern? Yeah, it's called new buffered reader, new data reader, new file reader, and I see some of you laughing already. And you look at that example and you say, that's called decorator? Because the word in English is called ugly when you look at a code like that. And then you wonder why they would call it decorator pattern and show an ugly example. And we never ever use decorator pattern ever again, isn't it? Because that code is a monster, and anybody tells you you can use decorator, you start laughing at that point. Well, that's a really terrible example of decorator pattern because that noise completely drowns the benefit of decorator. But thankfully, we don't have to do that now in Java thanks to lambdas. But more important than lambdas, there is something else that's absolutely important. And that is, one of the key things about functional style of programming is not the fact that you can use lambdas, but the fact that you can compose functions together. And composability is one of the most essential characteristics of functional programming. So to understand composability, I want to give you an example right in here. Suppose I write a function called printed, and the printed function takes a number. It takes a message, we'll say message, but it also takes a function which takes an integer and returns an integer. We'll call it func. So we have these three things that we're going to pass to this function called printed. And within this, of course, I'm going to bring in function star. Now what I want to do is I want to simply print out right here, and I'm going to say n plus, and of course we'll say 5, and then we'll print the message, if you will, and then we will say a colon after this, and then we will print right here func.apply, and we'll pass the number to it. So I want to use this function to get some work done. So what am I going to do now? I'm going to say here function to begin with, and this function, let's say integer comma integer, we'll call it inc is equal to, given an element, return element plus 1. So now I can simply call printed, and the printed function simply says 5 comma incremented, and I'm going to simply call inc on it. And as you would expect, what does it do? 5 incremented is 6, and tells you that the value of 5 being incremented is actually 6. Great. I can similarly come down here and take a 10. 10 incremented is 11. Well, that's great so far, isn't it? Now what I can do is create one more function here, and the function is going to take an integer, return an integer, but this time I'm going to say doubled is equal to, given an element, return element times 2. You know where I'm going with this. I can simply say now 5 doubled is going to be doubled, and similarly 10 doubled is going to be doubled as well. And 5 is doubled becomes 10, 10 becomes doubled becomes 20, and you can see 5 doubled and 20 doubled. But what do I really want to do now? Now I want to say printed 5 comma incremented and doubled. Oh dear, how do I really do this one where I want to increment it and then I want to double it? Well, here's an idea. What I can do is I can create over here function integer, comma integer, and given an element, this is going to be inc and doubled, and then equal to, I could say e plus 1, and then times 2 over here. Now, if I do this, what is the consequence of this? This means no friends, isn't it? Because we just duplicated more code. Nobody's going to just hang out with us after this, and they will get together and talk without us and say, that's how he's writing code. This is not the way to get around. So what are we going to do? Well, the good news is we don't have to go that route. We can beautifully have composability. So inc and then, so we can say and then doubled, and we can compose that very nicely. Isn't that cute? So what you can do is you can take the increment function, and you can do an and then on it, and you can pass the double to it, and as a result, now you have a function that is composed of these two other functions inside of that. And that is a pretty charming capability where you are able to compose things together. So in other words, what you just did is you took one function and you composed another function with it, and now you have a bigger function that is a combination of the two functions put together. So that gives you the ability. So when you make the call on this function, that is going to execute this one, pass the result to the next function, which executes this next function and gives you the result after that, and that becomes your abstraction to move forward with it, and that becomes extremely powerful. Well, now that you saw how you can combine this, we can now start decorating our code with combinations of things like this. Let's entertain a thought about how we can actually achieve that and combine functions together to put something together. So let's start with a little example to play with it. Let's say we want to create a class called, let's call it as camera right now, and the camera function is going to contain a function which is going to be public, let's call it color, and this is going to be snap, which takes a color, let's say input, and it's going to give us a snap of the color with the output. But what do I want to do with a camera? Well, typically when you look at a camera, what people normally do is you have a nice camera, but you put filters on the camera. Now, I have a camera which is, maybe relatively fancy, but not too fancy. But I want to take a picture of a mountain. Most of the pictures you see behind are the things I've taken. But I would bring in a little filter so I can take a much crisper image of something in the distance. But then I would remove the filter if I'm in a small room and I want to take a picture of somebody who is close by. So in other words, you can start putting filters around a camera. That's an example of using a decorator. And that's exactly what I want to do here. So what I want to do is to say function right here. You know what? We'll start with baby steps. Let's simply return the input for now. So it just takes an input and returns that output. But let's go ahead and play with it. So public static, let's say, void printed. And the printed is going to take a camera. So we'll simply say camera. And all it's going to do is simply output, let's say, camera.snap. And it says new color. And in this case, we will pass to it 125, 125, and 125. Now, what in the world is that color? I know that's a bit scary, but that's java.awt.color, let's say. So I'm going to just pass that color to it. And all that the printed is doing is simply printing out the color given to us. Now, what do I want to do? Let's start with a little example. We'll call it printed right now and pass new camera to it. And all you would expect it is, in this case, simply print out the result of that particular call, which should be the colors we provided. That's all it did. Great. But then what I want to do is to apply a filter to it. So the way I'm going to apply the filter to it is I'm going to call printed new camera, but I'm going to pass a filter. The filter is called give me a color as an input. I want to return a color dot brighter. So in this case, I'm going to call the brighter to return the color as a brighter color than what I provided. Well, before we go any further, I can refactor this as color : brighter, like that. So this gives me an ability to pass a brighter color as a filter, so the color given will be brighter when I get it as an output. How would I really implement this piece of code? I'm going to go to this code right here, and I'm going to first of all bring in a function. So in this case, I'm going to say private function, and this is going to take a color as an input, return a color as an output. We'll call it a filter. Notice I'm using the word filter as a singular right now. So then what I will do is write a constructor for the class here, camera. This takes a function color, color as an input. And I'm going to say a filter. We'll call it filters. Filters as a plural. So I'll pass a var arg to it. And then what am I going to do right in here? The first thing I'm going to do is filter is equal to, given an input, return the input back to me. So I'm assigning a very trivial filter, an identity filter to this. Given an input, it returns an output. Then I'm going to say for, and you know where I'm going with this, right? Function color, color, and I'm going to say over here a filter. This comes from the filters given to us. Then I'm going to say filter is equal to, and I can say filter, and then I can simply add a filter to it. So this combines the filters given to us to form a bigger filter. So if you pass 0 or more filters to me, the filter field is going to be a reference which may not hold anything other than an input is going to be output, or it may hold a reference to one filter, or it may hold a reference to two filters put together. So this reference may have really one input to output, or one more, or a combination, and that's what line number 12 is doing, is combining those filters together to form that pipeline of those filters. Now that we created it, let's see what the output is going to tell us right now. Let's go back over here and make that code to work. So when I run this code, what does it do? I got a bunch of warnings right now. This is what I love about Java, right? So we can quit doing real work and make the compiler happy right now. So what are we going to do now? we're going to go to this code and say, oh, there's a warning on line number 8. Let's fix that. What do? We will use this beautiful feature called suppress warnings. What is really cool about it is suppress warnings, not just one warning, right? And then what are we going to suppress over here? Maybe we'll do unchecked over here, and we can say, provide whatever that we want to provide and ask it to deal with it. So we can specify suppress warnings and get rid of it, and that way you can remove the warnings. I'll let you do that if you're interested in it, but let's get to the code itself and run that. Now at the bottom you can see, what is it going to do? We need to apply the filter, isn't it? Let's apply the filter. So I come to the line number 18 and say, what am I going to do now? Return the filter.apply and pass the input to it. So when you run the code this time around, you can see the first one is 125, the second one is 178 because it's brighter. Now you know where I'm going with this. We can take this one and say darker, if you will, and of course, it's going to be a little darker. And if you look at the output in the very bottom, you can see that it says 87. So that shows you that it's a little darker than what was given. But now let's come to the actual decoration aspect of things. What you can do is you can say brighter, comma, and you can put a darker. So now you can start combining different decorators to it. So this says, given a camera, take the input coming in. I don't know why, but you would want to make it brighter, and you're going to make it darker. Now, in theory, if you make something brighter and darker, it should be the same as input, but theory never meets practice that way. So when you run this code, what is the output we're going to see right now? You can see it's 124, 124, and 124, but it essentially shows the code actually worked. And that becomes a nice way to do the decoration. But I'm going to show you one more thing really quickly. If that worked really nicely, I'm going to refactor this code a little bit to make it a bit more functional. Some of you may have realized what I've done here is an operation called the reduce operation. So here's what I'm going to do to fix this code to a functional style. I'm going to say filter is equal to, I'm going to say stream. First of all, let's bring in the stream. So we'll say stream right here. So this is going to become a stream dot. So stream, this code right here, will say stream dot off. And what is this? This is going to be filters that we bring in. Then I say reduce. And the first thing is, given an input, return an input. Then we say over here filters, comma. Well, this is going to become, we'll say a filter, and then we would say, in this case, result, and simply return from this the result over here, dot and then, and we will say a filter. So this really brings ability to combine all these filters together to create our filter. Well, what does this do? You can see the output from the bottom. It still worked. If you're happy with that, we can refactor this one more time right in here. And we can then say, what in the world is this? That's a function dot identity. That's what it really is. It's an identity function. And then you can say, this one right here simply is a function double colon and then. And so you can refactor that code pretty effectively to reduce all that clutter. So rather than writing the code at the top, you can refactor that to a very sweet little reduce function. And as a result, you're combining those objects together, and you're forming this pipeline. So that's an example of using a decorator pattern, using Lambda expressions and method references. And of course, on the caller side, you can see how easy it was to invoke this, simply passing to the constructor a list of function references, method references, which are comma separated, and that becomes a nice way to decorate it. And that's an example of how you can use the decorator pattern with lambdas and method references. Well, the next example I want to show you here is going to be one that makes the interfaces much more cleaner. And for this, I will take an example of a mailer class. Let's say the mailer class contains a bunch of functions. A public void from, which takes an address right here. We'll call this as some kind of a function address. And all I'm going to do is simply output right here a from. Similarly, I'm going to have a few other functions. Let's call this to. Let's call this body. Let's call this one as, from to body and subject, let's say. And then finally, of course, we will simply say send. The send is not going to take any arguments right now. We will simply say over here sending. But this one is going to say body right here, which is going to be some kind of a text. Subject is going to take a line, but that's going to be subject. And to is going to take an address, and we'll say to. But how do we use this particular class in our code? Well, to use this class, a traditional way of doing this is mailer is equal to new mailer. And then you can say mailer.from. Who is this from? Well, this is from builder at, let's say, agiledeveloper.com. Who is it sending it to? Well, let's say it's actually sending it to my email address. Mailer dot, let's say, subject. This is a subject. I get an email every single day from my build system. It politely tells me or impolitely tells me, your code sucks. And then it, of course, tells me not just the detail about it sucks, but it also tells me how it actually sucks today as well. So there is a little bit more details about how my code sucks today. And then, of course, finally, a send method to invoke it. Now, when you look at this code, what is that called? That's called Java code, isn't it? Because that's noisy and so fluffy. But there are two problems with this code. The first problem is, hey, what do we do about all this noise? The second is, should we reuse the mailer in the end, or should we not reuse the mailer? There is no real good answer to it. And the worst answer you can give to people is, go read the documentation. How did that work out the last time you tried it? Because documentation usually says exactly what the function name says. It's very frustrating. Well, let's solve this problem. What can we do? Well, a couple of things we will do first to reduce the noise. The first thing is we'll go back to this code and take these functions, and we will have each one of them return a mailer back to us from those calls. And as a result, what we will do here is take each one of these lines and return a this at the very end of these calls. So every single one of them simply return the current object back to the caller. Well, now as a result, we can go back to this code and we can simply say mailer.from, but we can remove this noise from here, and as a result, we can remove these semicolons as well, and the code still works. So that's one way we can reduce the noise, and this is called the compose method pattern. But then we can take that to the next level, and what we can do is make the constructor private. So we can say private over here, mailer. And now that the constructor is private, you no longer can create the object on line number 14. So what do? Mailer.use. And within here, we'll pass the mailer to this. And then, of course, we will simply say over here, mailer.from. And we will actually, rather than use, we'll call it as send. And then we will simply call all that method up to here. So mailer.send takes a lambda, which receives a mailer, but then we call the from, the to, the subject, and the body from that function. So as a result, the send function became a static method. And what are we going to do within this function? Within the send, we are going to say mailer is equal to new mailer. And then, of course, we can say block.accept and pass the mailer to it. So now that we are doing the code this way, how does this help us? We can then go back to this and say java.util.function.consumer, and we can bring the consumer in. And this becomes a consumer of mailer. We'll call it as block. So when we look at this code now, the send method right now is receiving a lambda as an argument. Then we are saying on line 20, mailer.send, it takes a lambda, it takes the mailer, and then we can do whatever operation we want to do with it. But when we return on line number 24, we go back and complete the operation on line number 14. So as a result, we have removed that noise in the code, first of all. The second thing is, should we reuse the mailer or should we not reuse the mailer? Hey, I don't need to worry about it, because the designer of the class can take care of it. If they don't want us to reuse the mailer, they can create a mailer every single time. If they do want us to reuse the mailer, they can maintain a pool and give us an object from the pool. As a user of the object, I no longer have to be worried about it, and that's not a concern I need to carry around. Well, the ExecuteAround method pattern is a very similar pattern. I'll just mention it right here. We're going to use a very similar approach like what we saw just now, except that in this pattern, the goal is to do a pre-op and a post-op. So where we have the send method, we can do operations before we call the accept and operations after we call the accept, maybe within a try and finally block. And basically, that same example can be extended to the pattern called the ExecuteAround method pattern. So to summarize what we talked about, we saw quite a few design patterns in here. Some of those patterns are the patterns from the days of design patterns book. While these are traditionally written using classes and interfaces and objects, those can be written using lambdas. Your design patterns shrink in size. You don't have to implement classes and interfaces and all that fluffy code as we once did. We can write a lot less code, and we can leverage lambdas to really achieve that particular fluency. And some patterns, like ExecuteAround method pattern and the fluency that we saw here, where things we normally didn't do in Java, but now we can do thanks to availability of lambdas. So the old patterns, some of them are quite a few of them, become a lot more fluent, and some patterns that we once did in other languages can now be brought over to Java as well, and we can benefit. If you're interested in the code example that I showed you, you can download that from my website, agiledeveloper.com. I hope that was useful. Thanks for coming.
Thank you. Any questions?
There's one over here. Thank you.
Thank you. One question will be about decorating pattern. So let's say that we have a lot of code, a lot of functions, and its compositions. And did you get experience with debugging this code?
So the question is, how do we go about debugging this code?
No. How hard is
How
debugging
hard
this?
is it to? I don't spend my day writing bugs, so I don't know the answer to that question. No, just kidding.
I had, sorry. And it's very hard to debug because everything that you have is a stack trace with and then apply, and it's a lot of 100 stack trace of these names, and you don't understand in which place you need to go deeper and
So I'll give you two answers for that question. The first is, when I was a very young programmer, I used to live within the debugger. This was like being stuck into a debugger, right? That's the life of me. Once I started embracing test-driven development, honestly, I do a lot less debugging than I used to. I'm not telling you I don't use a debugger at all. But what I do today is if something is not working, I put a debug in my test, and I start stepping through. I can tell you how many times within seconds I'm like, oh, darn it, I know what the problem is. So the first is, the key to debugging, there are two keys to debugging. The first is cohesion. If you make the code very small, it becomes easier to understand, easier to debug. The second about debugging is, it's all about understanding the semantics. Once you understand the semantics of the code, the lazy evaluation, and the sequence in which it is going to go from one to the other, you know what to anticipate, and the debugging becomes very easy. So when people tell me it's hard to debug, I'm not saying it's not hard for you. It was hard for me also, but once I got comfortable with the semantics, debugging become a lot easier. So the first is get very comfortable with the semantics, and the second is embrace automated test a lot more, so the debugging need becomes a lot less, even though it never goes away. Yeah. And that's good, that's great, better than never. Yeah.
Thank you. We're running out of time, so now it's time for coffee break. Thank you.
Thank you.